Hello everyone. So today is the last class and the 12th installment of the course entitled as Transition Metal Organometallic Chemistry, its principles to applications. So I am Anubhav Nath. I am a PhD student in the Department of Chemistry at IIT Kanpur. In my fourth year, I am doing my PhD. And today I have actually basically revised some basic problems on this organometallic chemistry, so that by going through which we will have a brief idea on the reactivities or on the basic bondings and the other aspects of this organometallic chemistry. In the last class, I have actually basically taken up transition metal olefin complexes, diolefin complexes, or alkyne complexes as a major topic of discussion. And I will discuss about their reactivity, their change in bond order, or their complexes corresponding, or some basic reactions. So depending on that, you will have a brief idea on the species. So we shall start accordingly. So the first question is identify the incorrect statements in the change in bond orders in the transition metal butadiene complexes is better ascertained by change in CC bond lengths, the 1J 13C 13C coupling constants, the 1J 13C 1H coupling constants, the mass spectrometry. So which of these four options, which among all these four options is incorrect? So you have to basically go through the question very carefully, because in some competitive exams you will see like you mistake it like it's a correct statement, so we'll take the correct statement, and you will have some multiple choice for multiple MSQ type of questions. So here you have to be very careful while answering, because it's an MCQ and it is bold and underlined here because it's the incorrect statement they are asking for. So one by one, we will go through each of the following options. So firstly, change in the CC bond length. So the two species here are actually can be termed as transition metal, that is MLN, where L is the other ancillary ligands, and the butadiene. Butadiene is nothing but CH2, double bond CH2, double bond CH, double bond CH, bond C double bond CH2. So this is actually a 1B butadiene. This is the simplest butadiene we have taken here, for example. So whenever from a butadiene there is a conditional metal complex, the electron flow goes from the butadiene to the transition metal, because metals are electron deficient, and this ligand is actually able to donate the electrons to the metal center. So what happens in this case, whenever a butadiene or any such ligand is delivering the electron to the transition metal, then there will be some change in the bond length, because you see, whenever when the electron is flowing from the donor moiety, that is the butadiene, to the transition metal, what happens in case of this butadiene actually devoid of the electrons. So number of electrons in the LUMO or the LUMO in the HOMO of this butadiene gets suppressed, because this is actually getting donated to the metal center. That's why the bond order will change whenever a butadiene complex will donate, or any such ligand complex will donate the electron to the metal center. So what happens in the butadiene framework? In the butadiene framework, there are several CC bond lengths, so their bond orders will be changed, they will be perturbed, and so the corresponding bond length change will also be observed. So that's why you will see some significant change in the CC bond lengths whenever a transition metal butadiene complex is formed. In case of coupling constants, whether it is a proton 13C coupling constant or is a 13C coupling constant. So in those cases, actually, we will have a brief idea that they will also be changed, because in that case, whenever a electron is getting delivered to the metal center, there will be a charge separation in the butadiene. So whenever a charge separation will occur in the butadiene, so there will be development of some del plus charge in one carbon atom. In the adjacent carbon atom, there will be development of a del negative charge. So then the coupling constants will differ between the protons, because the chemical environment around that particular proton or the nuclei that we are concerned about will be changed. That's why their coupling constants will be changed. This will be a significant tool to actually identify whether a transition metal butadiene complex has been formed or not. So options B and C are also correct, because there will be a significant change in the J value. I have already told that there will be a change in the CC bond lengths significantly. Now let's come to the last point. So what happens last point? Last point, there will be a transition metal butadiene complex, whether the mass spectrometry will be able to ascertain this change in the bond order. So whether mass spectrometry will be able, whether in case of mass spectrometry there will not be any change, because mass spectrometry will not be able to tell us whether this complexation has occurred or not. Because if we have this butadiene and the transition metal in a separate entity, so their mass will be some x plus y will be something. So this value can be denoted as A. And when transition metal butadiene complex will be formed, since it is an addition kind of reaction, because butadiene is a neutral moiety, so this will be added to the transition metal. So then also you will see that the total mass will be that previous one, that's like the previous one, that is x plus y will be equal to A. So mass spectrometry will not be able to actually tell us that whether this transition metal butadiene complexation has occurred or not. So the correct option is option D, that the mass spectrometry will not be able to ascertain the transition metal butadiene bond order change, because the bond order change will not be reflected in mass spectrometry, because in that case only chemical environment around that proton or this ligand framework will change, and so the entire mass of the compound will remain the same. There will be no chemical change, so that this one of elimination of several product or other thing will happen, so that mass spectrometry can actually tell us whether this molecule is losing something or gaining something, or the entire phrenology around the complexation framework is actually happening in what direction. So mass spectrometry is the correct answer here. That is an incorrect state in change of bond order determination by mass spectrometry cannot be done. So in the next question, it is a late electron rich transition metal complex of a conjugated diolefin is known as. So in the last question, I have actually told you that butadiene is also a conjugated diolefin. It's a 1,3-butadiene that they are actually conjugated, and so that they are resonance stabilized. So here a late electron rich transition metal complex of a conjugated diolefin is known as which of these following options? First one is the pi complex. Second one is the metal sigma alkyl complex. The third one is the Pinzer complex, and the last one is the metal cyclopropane. So the correct answer is option A, a pi complex. A pi complex is the correct answer here. So we will discuss why it is so, and we will discuss each of these following complex. Whenever a pi complex is concerned, pi complex is nothing but pi electrons will be actually be able to donate the electrons. The pi electrons will be involved in bonding to a transition metal only, not the other cases. So here there will be a no sigma bond formation between the metal center and the ligand center, or that is the conjugated diolefin. So only the pi electrons of the diolefin moiety will be bound to the transition metal. Second one is the metal sigma alkyl complex. In case of metal sigma alkyl complex, there will be a sigma bond between the metal and the alkyl group. So here no pi electrons will be actually no pi electrons will be involved in bonding, because there occurs a direct sigma bond between the metal center and the alkyl group. This can be methyl or ethyl or any allyl group also. So there will be a sigma bond formation between the metal group and the sigma alkyl group. A Pinzer complex. Pinzer complexes are actually very well known metal complexes in terms of bonding, in terms of organometallic chemistry and catalysis also. In Pinzer complex, there will be 3 coplanar donor atoms. So they will be donating or chelating the metal center in a meridional configuration, not in a fascial configuration. So in that Pinzer complex, in case of Pinzer complexes, the donation of the ligand is very tight. So there will be occurring two such kinds of these ring systems. The major one or the most researched one is the 5-5. The ring size between these two ring of this donation will be 2-5-5. This can be 5-6 or 6-6. Such kinds of also known, but 5-5 is the most researched one or most abundant one. So in pincer complex, the metal complex becomes highly stabilized because the tightening tightening of the packing or the binding by the donor atoms of the ligand is very much well known and established. So in case of pincer complex, they are actually thermally very stable because of the tighter binding of the pincer ligand, and they are aerially also stable on the corresponding chelating bidentate complex. Pincer complexes are tidentate ones where different donor atoms can be. So several such kind of pincer complexes are known. This can be CNC or NCN, or you can say PCP. So such kind of donor atoms can be actually able to donate the electron to the metal center. A metallocyclopropane is quite different here. Here occurs a direct sigma bond formation to the metal to the two different carbon atoms, which are actually again bound to each other. So in metallocyclopropane, one of the carbon atoms, you can imagine like that, one of the carbon atoms you can substitute it by a metal. So MCC, there will be it's a M, C, and C. So MCC is a kind of metallocyclopropane. So these are the 4 types of complexes that actually given here. So which one will be called? So a late electron rich transition metal complex of a conjugated diolefin. So among all the examples that I have put through, only the first one is actually holding good, because you see it's a pi complex because it's a conjugated diolefin. So diolefin is only capable of getting their pi electrons only. So the pi electrons will be neutrally donated to the transition metal. So this will form an electron rich transition metal complex with a conjugated diolefin, is particularly known as the pi complex. Coming to the next question, this is not actually question. This is actually this is basically the understanding that we got from the last slide. I've actually summarized it here. So we shall go through each of the points one by one. So firstly, in an extended DCD model is nothing but this Dewar-Chart-Duncanson model. The 3 pioneer chemists in the field of the organometallic chemistry who have developed this bonding on the several kind of interactions or orientations of the orbitals, etc. in terms of organometallic chemistry. So in an extended DCD model, the bonding in this eta4 C4H6 M can be described by the following components. So from Dewar-Chart-Duncanson model or the DCD model, the bonding that is eta4 C4H6. C4H6 is nothing but this 1,3 butyrine kind of complex where this is an conjugated diolefin that we have discussed in the last slide. So all the 4 carbon atoms are actually involved in donating the electrons to the metal center. That's why it is an eta4 system. And there are 4 carbon atoms, C, 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 a double bond here, a double bond here. So this is a C4H6 system. So this can be described by the following components. So there are actually 4 different carbon atoms which are having 4 different orbital systems, the Psi1, Psi2, Psi3, and Psi4. The first one is the Psi1 to metal sigma. So first one is Psi1 is donating the electron to the metal sigma. Then the Psi2 is donating to the metal pi. The metal is actually having the sigma orbital and the pi orbitals actually. And second one is the back donation of the electrons from the metal center to the ligand backbone. That is a psi orbital. So M pi will back donate the electron to Psi3, and M delta will back donate the electron to Psi4. Now, both this Psi2 to M pi and this metal pi to Psi3, that is the pi electron donation. You see, whether in case of this or diolefin or olefin systems or pi bonded systems are concerned, in those cases, this pi electron donation will be the most talked one topic. So in this case, when a Psi2 is donating to the metal pi, so there will be a donation of electron from the HOMO to the LUMO of the metal LUMO. So that's why in this case the Psi2 is the HOMO, because Psi1 is the C4H6 totally having 2 pi bonds. So there will be 4 pi electrons. So there will be 2 pi electrons here in the Psi1 and the 2 pi electrons in Psi2. So Psi2 is the HOMO and Psi3 is the LUMO in case of conjugated diolefin system. So from the HOMO, there will be donation of the electron to the M-pi, and from the M-pi, there will be back donation of electron to the LUMO. So when a donation of electron is occurring from the HOMO, so bond order will be suppressed because the bond length will then it will be dropped, because the HOMO the electron density is actually not that much, it is decreasing. So there will be a decrement in the bond order. And also this from this M-pi to Psi3, there will be a back donation, that is from the M-pi to LUMO of this C4H6, that is eta 4 C4H6. It's a LUMO. So if the LUMO is actually getting populated by electrons, then the bond order will also decrease. So in both the cases, whether it's a HOMO to M-pi back, HOMO to M-pi donation, or the M-pi to Psi3, that is a LUMO back donation, both of these will result in the decrement in the CC bond length. That is, there both will be a decrement in the bond orders of that particular double bonds. So that bond orders will be effective in the lengthening of the terminal CC bonds, because the terminal CC bonds are actually having these pi bonds. That pi bond donation will be happening. That's why, since this is the system C C C C, so here in the terminal positions there are two double bonds. So when their back donation or this donation of electrons is actually happening, so what will be the case? There will be lengthening in the terminal CC bond. So in opposite manner, so in the same manner, the shortening of the internal CC bond will also occur, because if the two CC bonds in the terminal sides are getting lengthened, then also automatically the internal CC bond will be shortened. So that bond will be even more stronger. So this is the consequence of the depopulation of Psi2, because from Psi2 the electrons is getting thrown to the metal pi. That's why there will be depopulation of Psi2. There will be population of Psi3, because on the metal pi there will be a back donation of electron to the LUMO, that is Psi3, and the nodal characteristics of the ligand orbitals. In the next point, coupling constant, that is 1J 13C. In the 13C NMR spectra also give evidence for change in bond order for eta 413 diene ligand. Just in the previous slide that I have discussed, like 113, that is the coupling constant J value will be able to actually tell us to whether there will be significant change in the bond order or not. Because you see there are two dissonance canonicals that we have drawn here. You see here, this is the 1,3-butadiene system, is the eta 4 manner. It is binding to the MLN, that is a transition metal center. And if you see, there occurs a significant resonance structure we can draw. This bond will be pulled off here, and this bond will be done here, and there will be metal to sigma this bond. So M, this bond will be happening, and there will be a double bond here, and there will be a single bond here that will be bonded to the metal center. So this will be a characteristic to perform. It's a metallocyclopentene kind of system, where there are 5 members here. That is a cyclopentene. One of the member is actually metal, that is not a carbon, so it is metallocyclopentane. And since there is a one double bond here that is isolated, and that will be bonded directly to the metal center, because you see the position of the double bond is as such, it is actually trans or 180 degree opposite to a metal center. So direct bonding between this double bond and this metal center will be possible. So it is a metallocyclopentene, and it is metal eta 413-butadiene. So there will be a significant transition. Canonical structures can be done between these two intermediates. That's why the coupling constant between this carbon and this carbon, this carbon and this carbon will be quite different, because you see there will be 2 CsP2 carbons here, and these 2 CsP, all the carbons are actually CsP2, but here you can see there is CsP3 and this CsP3, and these 2 carbons are actually even coming closer, because you see there was a single bond here, but it is double bond here. So the bond length has shortened here. In this case, you see there are double bonds, so the bond length was low or short. Or in this case, there are sigma bond, so their bond length is quite high. It is double bond. So that's why from double bond they are coming to single bond. That's why the bond length will be lengthened. That's why there will be a significant canonical structure that can be done between this eta 413-diene and this cyclopentene kind of system. The terminal carbon atoms having this hybridization. So here you can see the terminal carbon atoms, that is this one and this one, this one and this one, is having hybridization state of in between sp2 and sp3. So in this canonical structure, the hybridization of the carbon is sp2, and in this canonical structure the carbon is sp3. That's why the actual hybridization of these states will be in between this sp2 sp3, that is sp2.5. so that can be actually evaluated by the basis of this coupling constants between 13C and 1H, 1J. The late electron rich transition metals designated as pi complex, that is actually reflected in the last slide, whereas the corresponding compounds of early transition metals designated as metallocyclopentenes. The late electron transition metal complex are actually general pi complex that I have discussed in the last class. But what happens when the corresponding transition metals are early? So when early transition metals are actually here, because scandium, titanium, or vanadium, or chromium, so they can actually have a significant sigma bond, so a significant sigma bond character with the carbon atom. That's why they prefer this canonical form, but the early transition metal prefer this canonical form. So late early transition metals actually are favoring the metallocyclopentene kind of system, but in case of late transition metals, they are actually favoring this eta 413 butadiene kind of systems. So in the last point, is actually quite clear that the late electronic transitional metal designated as will be pi complex. That is a pi complex. You see there is a pi donation of electron to the metal center, but in this case, this is the early transition metal. That the pi bond is not that much strong, so they will shift themselves to the corresponding sigma bond system to the metal center. That will be metallocyclopentenes. So let's come to the next question. This is actually showing some different binding modes of alkynes with transition metals. So the question is regarding the same, like showing different binding modes of alkynes with transition metals. So till now we were discussing about this alkene kind of system, or conjugated diolefin system, or several isolated olefin systems. So here now we shift to the last topic, that is the alkyne as ligands to the transition metals. So there are actually significant different coordination modes, various coordination modes available for alkynes to bind to the transition metals. We shall go through all of the cases one by one. The first one is the monodentate binding of the alkyne to the metal. Second one is also the bidentate binding. Here only the triple bond was able to get attached to the metal center, but here you can see this is a bidentate binding. So both of these carbon atoms are actually involved in binding to the transition metal. In both the cases, the donation of the ligand property is actually 2 electron donor. The metal fragment is M here, that is electronically rich. So electronically rich metal system, that is the late transition metals, will be actually prone to have such kind of binding, where is a monodentate binding, and is only the pi electron will be available to bind to the metal center. And next one is a bidentate binding, where both of the carbon atoms will be bound to the metal center. The next one is the electron poor system, that is the electronically deficient transition metal system, that is the early transition metals. So chromium, molybdenum, tungsten, scandium, titanium, vanadium, such kind of metals will be preferring this kind of bonding. So first one is the bidentate one. You see here, since they are actually electronically poor, so the urge for electron is much more in case of these electronically poor transition metals, the early transition metals. So in that case, this is actually same as this one, but here you can see the double bond is actually also donating to the metal center. So it is bidentate, but the electron hunger for this metal is actually very much. So that's why this pi bond is actually again donating to the transition metal. Here is a bidentate one. Here there is a metal-metal bond, but you see the triple bond is actually equally shared between these two metal centers. This is also a bidentate kind of system. In all the cases, you see the olefins are actually, alkynes are actually 4 electron donors. Here 2 carbon atoms are donating 2 electrons, and for pi bond there is a source of 2 electrons, so total 4 electrons. Here also, both of the pi bonds are actually involved in bonding to the metal center. So it's a 4 electron donor. It's a tridentate kind of binding. The 2 carbon, this metal center is actually taking up electrons from both of these carbon atoms, but this metal atom is isolated, and it is actually having a different nature from this metal atom. This metal is actually only taking up the electron from the pi bond. That's why it's again a 4 electron donor. This one is a tetradentate system. Here you can see both of the metals are actually involved, both of the metals are equivalent, and they are having a significant interaction with both of the carbon centers of the acetylenic system. So in this case, it is also a 4 electron donor, and it's a tetrahedral system because the metal center is actually bound to both of the carbon centers, and this metal center is also bound to both of the carbon centers. So this carbon is tetrahedral, this carbon is also tetrahedral, so it's a tetrahedral kind of system. So electronically poor early generation metals will be prone to get bonding, get stuck in bonding with the alkynes by this 4 electron donor moiety, because they are electronically poor, and electronically rich metal fragments will be preferring this monodentate and bidentate kind of coordination mode only. So coming to the next question, it is the predict the product of the following reaction when this Na2PtCl4, there can be K2PtCl4 or other S block element, is treated with this ditert-butyl acetylene in presence of any amine, that is RNH2 here, alkyl amine it is noted here, in presence of ethanol as solvent. So what is the product of the reaction? So you see, this Na2PtCl4 is a very well known compound. We have actually previously discussed about this compound much more. Like it is actually this similar compound K2PtCl4 is actually one of the precursors for this famous Rice's salt. Just one second. So this Na2PtCl4 is one of the major K2PtCl4. That's the potassium version of this same salt. Is very well known compound to initiate a reaction to produce this Rice's salt. So here Na2PtCl4 is there. It is nothing but 2 sodium plus and PtCl4 2 minus. It's a square planar complex where platinum is there, and there are 4 chlorine atoms bound to this potassium center, this platinum center. Pd2 plus is a D8 system. So what happens in this case, when this ditert-butyl acetylene is given in presence of this strong nucleophile, that is RNH2. So RNH2 is a very strong nucleophile because there is a significant concentration of negative charge of the lone pair is accumulated in on the head of nitrogen. So nitrogen is nucleophilic in nature, and there are good living groups in terms of Cl minus. So RNH2 will preferentially attack on this platinum center to eliminate one of the Cl minus as NaCl. So there will be a bind. So this RNH2 is actually bound to this platinum center. So you can see, and there one of the Cl minus will be eliminated. So again, so 3 Cl minus will be also there. So the other Na plus will be capturing this other Cl minus in terms of NaCl, and this will also be eliminated. So 2 NaCl molecule, 2 moles of NaCl will be eliminated from this center. So platinum will be left with 2 Cl chloride moieties or atoms. So they will be trans to each other to minimize the amount of this steric hindrance, because they are quite bulky in nature. And since you see the RNH2 is there, and it is actually going by a nucleophilic attack on the platinum center to eliminate the Cl minus. So on that vacant position only, this acetylenic system will come and bind to the platinum center. So this is the platinum 2 system. So no redox reaction is actually happening here. It is a normal substitution reaction where this RNH2 is actually nucleophilically attacking on this platinum center, which is quite electrophilic in nature, and in the opposite trans position to the Cl minus, that is actually getting evaporated NaCl or sodium chloride. So in that position, the ditert-butyl acetylene will come and bind to the olefinic center. So you see, this is platinum 2 because the 2 chloride atoms are there. So platinum 2 is the 8 system. So 8, 2 electron donors, 2 electron donor, this 2 electron donor is also a 2 electron donor. So 2 plus 2 plus 2 plus 2 is 4, is 8, and platinum is a D8 system, so 8 plus 8 is 16. So this is a 16 electron square planar complex where you can see there the bond angle between this carbon and dibutyl group is not 180 degree, unlike the acetylenic moiety, it is rather 165 degree. So there is a significant tilt of this butyl moiety from the platinum center to the backward center. That's why the angle is now short. The angle is shortened because you see here there should be ideally 180 degree, but since this bulky metal framework is actually present here, that's why that butyl group is not here. It actually tilted backwards or dragged backwards from the platinum center. That's why the angle is 165 degree. The bond length will also be decreased because this is actually donated to the platinum center, and the back donation will also occur. So that is the bond length is 124 picometer. The new CC is actually also dropped because it is actually nearly it is lying in the range 2200, but since the bond order is dropped, the new, that is the IR stretching frequency, now is 2028 centimeter inverse. This example is actually taken up from this famous scientist Chat's work. So in 1961, firstly, this is a homoalkyne complex. Here is a homoalkyne complex. Two groups are same as a 2 electron donor, and this is a preparation by substitution reaction because this RNH2 is the nucleophile here. Coming to the next question, predict the product of the following reaction. Is CP2TiCO2 is getting reacted with this diphenyl acetylene in heptane solvent at room temperature for 3 hours. So what is the product? The last slide, actually one point maybe I have missed out. In the last example I have actually told you like the early transition metal will prefer this 4 electron donor kind of binding, but the late transition metal will prefer this 2 electron kind of binding. You see this platinum 2 center is a late transition metal, that's why it is preferring the 2 electron donor mode or binding mode of the alkyne, unlike the chromium or molybdenum or titanium kind of systems. The next example is CP2TiCO2. Titanium is in class 2 state. So titanium is a 2 electron system because class 2 state is 2 electron, and CP2s are actually 6 electron donors. So 2 CPs are actually 12 electrons. 12 plus 2 is 14, and 2 COs will donate total 4 electrons. So it's an 8 electron compound. So this 8 electron compound is treated with this diphenyl acetylene in heptane solvent. What is the product? So this is a heptane solvent, and vacuum is actually the reaction occurs in vacuum because in this case there are actually COs, and COs will be liberated in presence of vacuum only. That's why the reaction is actually taking place in vacuum. So here there are 2 CO molecules that are present. One of the COs will be eliminated here in presence of vacuum. So see that there are 2 CPs are actually bound to this titanium center, and you see since this diphenyl acetylene is given, so diphenyl acetylene will actually be bound to the corresponding system. So you see this CP2Ti diphenyl acetylene is actually given. So you see there is a CP2Ti moiety is there, and one CO has been eliminated. So one CO is remaining here. So the diphenyl acetylene moiety is here, and you see the angle between the CC and the CPH bond is actually not even close to 180 degree. It is nearly 146 degree. So it is nearly 34 degree decrement in the bond angle of the CC the bond. That is actually same as the last one because you see there is a significant metal center and sterically hindered metal center here. So there will be significant steric hindrance with this phenyl moiety, with the CP minus moiety. That's why the CPs are actually dragged backwards from this titanium center to minimize the steric hindrance. That's why the angle between this is 146 degree. You see here these 2 CC bodies are actually not only donating the pi electrons, also donating the pi electrons in the bidentate manner. Bidentate manner, this titanium center is getting bound to the additional metal. That's why this new CC is actually in the range 1780 centimeter inverse. So you see the CC bond order is even dropped here. That's why the bond length is again even short. The bond length is 128 picometer, not even too close to the standard of normal CC triple bond. This is not in the state of CC triple bond even because it is totally getting bound to the titanium center. It is this specific example is also taken up from Mr. Floriani. The work was done in 1978. this present example. Here also you can see this alkyne complex is actually getting formed with concomitant release of this neutral CO. In the next example, we're actually coming predict the product of the following reaction. This is a tungsten hexachloride or hexachlorotungsten in tungsten in +6 oxygen state is reacted with this dichloroacetylene 1,2-dichloroacetylene dot ether complex. This is a very explosive complex one in presence of this tetrachloroethylene. So both dichloroacetylene and tetrachloroethylene are actually given in the reaction. So the corresponding reactants are hexachlorotungsten. So what is the product? So hexachlorotungsten is treated with this C2Cl2.Et2O in presence of this C2Cl4. So there will be a release of this neutral ether complex, ether compound, and also neutral this C2Cl6. So from C2Cl4, it is actually taken up these 2 electrons. So that's why 2 Cl atoms will be actually taken up from this C2Cl4. That's why it will be eliminated as C2Cl6. And this C2Cl2 will be bound to the corresponding tungsten system. There is actually a dimeric kind of system because there are 2 similar systems are actually taken up here. There occurs tungsten Cl4, C2Cl2 are actually a dimeric system. So when they are treating it with PPH4Cl, which is nothing but this PPH4 plus and Cl minus, this PPH4 comes as the counter anion because this entire system is negatively charged, because tungsten here it is it's a dinegative system, because you can see here C minus and C minus are there because they are tridented in nature. This is C minus, and they are actually having 5 Cl minus. So there are 7 negative charge, and so there is a +6 system. So +6 minus 7 is -1. That is actually counter stabilized by this large PPH4 plus or tetraphenyl phosphonium kind of system. Since this anion is quite large in nature, that's why these PPH4 plus systems are actually taken up here. So PPH4 plus is such a large counter cation, so this will be stabilized by the corresponding large anion. And this specific example was taken up from Deinike in 1986. He has done this splendid job of this paper. So here let's come to the last example also to actually account for some basic tricks. So here you can see this CP minus, and also they are actually having this C minus also. That's why it's a titanium +4 system. So from titanium +2 we are going to titanium +4 system. So it is a G0 system. So 6 plus 6 is 12, 12 plus 2 is 14, and this is actually having these 2 electrons, 16. So this is a 16 electron compound. So from 18 electron compound we're going to the 16 electron compound. 2 electron reduction is taking place here. That's why this is a specific example. In this example, you will see that there are 2 chlorine atoms are actually are going tilted backwards, because they are not actually able to tolerate the steric ignition from this large tungsten Cl5 system, WCl5 system. So these Cl atoms are dragged backwards from the olefinic or this acetylenic moiety. So that's why the angle between this is 144 degree, very less compared to 180 degree. Also, the bond order of this CC is even dropped because there is a electron flow from this CC triple bond to the tungsten center, that is a 128 picometers. This PPH4 plus system, nothing given because it is such a large cation, this will be able to stabilize this large anion. So firstly, the stability of the transition metal alkyne complex increases with increasing electron withdrawing character of X in XC triple bond X. So here that's why the such electron withdrawing chloride atoms are actually given here, for example. So even so, if fluorine was there, fluorine would be even more stabilizing, because here it is stability depends on the electronegativity of the corresponding substituent. And these are the highly explosive hydrogen substituted acetylenes in the uncomplex state can be stabilized by complexation. You see, because it is C2Cl2 is a very unstable compound, and this is in the uncomplex state. There is a highly explosive nature it contains. So when it is complex with the corresponding early transition metal, that is the tungsten, this bond is actually stabilized. So entire compound can be then captured or stabilized by complexation. So this is one of the major examples or the major applications when this transition metal complexation can be used to stabilize these highly substituted, highly explosive kind of compounds. The next example is show examples where a relatively unstable molecule becomes stabilized upon coordination with a transition metal. So here's the example. Here it is given this 1,2-dibromocyclohexene. It is treated with this PTPPH3 whole 4 in presence of reducing agent sodium amalgam. So what is the corresponding product? So you see, because the corresponding compound that is concerned here is cyclohexane. So in cyclohexane you can think of a triple bond here. So there is in cyclohexane this is actually remaining in chair fashion. So yeah, chair conformer, this is like of this. In chair orientation, the bond angles will be not even close to this 180 degree. It will be in between this 110 to 130 degree. So in case of cyclohexene, the bond order is actually close to 100. The bond order requirement is 120 degree. But when cyclohexane, we think of a triple bond here. So there you can see the angle between these two angles, and these two angles are actually not even close to 180 degree. The angle lies in the range 110 to 130 degree. So there occurs a significant kind of torsion strain, or you can say dihedral angular strain in such cyclohexane moiety. So in case of cyclohexane, the molecule in its free state is actually not isolable or very, very unstable. So here what happens, the sodium amalgam is actually a reducing agent. The sodium actually takes up this bromine atom, and in case of this Br, so sodium bromide, so there will be this bond will rupture to this bond, and this bond will be broken to again eliminate another sodium bromide moiety. So it will be a two molecules of NaBr will be eliminated. So that's when this compound will be treated as this cyclohexane. At once it can be complex with this PTPPH whole 4 moiety, platinum PPH2 platinum 0 system, which is having this 10 plus 4 PPH3 molecules are actually there. So 4 into 2 is 8 plus 10 18 electron system, quite a lot. So there will be elimination of this neutral PPH3 ligand dissociation will take place, and then these two carbon atoms will be donated to the electron donated to the platinum center. You see this angle between this carbon and this one is 127 degree, that I have told earlier. That angle lies in between this 110 and 130 degree, but the molecule in its free state is not very much stable, because alkynes demand the angle as 180 degree. But since you can see that even though it is 127 degree, this compound is stabilized because it's coordinated to the platinum center. Platinum is in class 2 system here. You can see the bond length is actually even suppressed. It is 129 picometer here, and the scenes, even though the bond angle is quite low from 180 degree, if it is 127 degree, it is a several 53 degree decrement in the angle. So the 53 degree angle requirement is even cannot destabilize this molecule because it is complex with the platinum system. This work was again done by Wimp in 1971. So here the sodium is actually reducing this system by eliminating 2 moles of sodium bromide. So the sodium is a reducing agent. So this platinum 0 is there, and it is 2 molecules are actually remaining. So these compounds will be electronically enriched. So this will be bound to the platinum center in this orientation. The unstable free cyclohexane can also be stabilized through transition metal alkyne complex. The stabilization is due to a distortion from linearity that alkynes experience upon coordination, which relieves the ring strain. Here, the ring strain was there because cyclohexane demand the electron the angle as 180 degree. But since this is electron donation, there will be distortion from the linearity, so that will relieve the ring strain. That's why this compound is stabilized, and this compound can be actually stabilized by this from the relatively unstable free version. So there are several such examples that we will be discussing on the same topic, like relatively unstable molecules, how can be stabilized. So in the next example, you can see this is a very famous metal complex. So the metal is niobium and tantalum. There are two methyl complex. They are both actually trans to each other. This one is cis2. This one is a CP star, and this is a metal phenyl complex. So whenever this compound is actually heated at 120 degrees Celsius, what happens? There will be elimination of this methane. So one of the carbon is actually bounded to the metal center, that is okay, but this carbon is actually having this metal hydride. This proton is actually having an interaction with the CH3. So this CH3 minus will be actually able to drag up this proton of this phenyl system, and it will be eliminated as methane. That's why methane elimination is taking place. High temperature is actually required to initiate the reaction. This minus charge that is actually happening here will then reorient itself to actually get bound to the metal center. So this is actually nothing but a carbine. So carbine, you actually the coordination of carbine, that is C6H4, which is not stable as a free molecule, can be stabilized through this transitional metal alkyne complex. You see the other ancillary systems are actually stabilized here. There is a CP, there are TA, and two CH3 molecules are here. The CH3 that is actually nearest to the methane center will be dragging up this proton and it will be eliminated as methane. The specific classic example was taken up by again the very well-known scientist Schrock in 1979. This coordination of benzene. So let's come to the benzene point of view. This is benzene, that is nothing but the alkyne. So the alkyne representation of benzene is the most widely encountered. Alkynes are usually described as having a strained triple bond. You see, there is an extra triple bond in the benzene system, that is you are denoting as alkyne. So alkynes, there are significant canonical structures that can be drawn in favor of this alkyne. So this is cumulene. You see the triple bond will be reoriented in this set. So the double bond will come up here, and the double bond will come up here. This bond will come here. So it will be cumulene kind of system. And the another system can be drawn as canonical structure in terms of biradical. So there this the extra bond, triple bond is here, can be drawn as two radicals side by side. That's why since two radicals are side by side, is a diradical kind of system, it is very, very unstable. So geometric constraints on the triple bond in benzene result in diminished overlap of in-plane pi orbitals, thus weaker triple bonds. The vibrational frequency or the triple bond in benzene was assigned by the famous scientist to be 1846 centimeter inverse. That is indicating a weaker triple bond than in unstrained alkyne with vibrational frequency approximately in the range 2150 centimeter inverse. So normal alkynes have this higher stretching frequency in the range 2150 or 2200, but in case of benzene, the corresponding triple bond length or the stretching frequency, you better say, is in the range 1850 centimeter inverse. So there is a 300 centimeter decrement in the vibrational frequency. That's why it is quite evident that this double bond is from geometrical constant is not that much stable than a normal free triple bond. Nevertheless, benzene is more likely a strained alkyne than a diradical, as seen from the large singlet triplet gap and alkyne-like reactivity. So benzene does not show actually this diradical kind of intermediate. Rather, it shows more of an alkyne kind of system, which is having a large singlet to triplet gap. In case of this unstrained alkyne, you can see the perfect angle is 180 degree, but in case of benzene, it is obviously less than 180 degree. It is in the range 130 to 150 degree. You see, there occurs a significant kind of overlap between these two pi orbitals of this olefinic CSP system, but in this case the orbitals are actually not planar. That's why there's overlap. The amount of overlap between these two orbitals is not the same. So that's why for all the cases, geometrical constants or the orbital orientation, all the cases does not go in favor of bonding or stabilization in case of benzene. That's why benzenes they're not that much stable, and they are not actually isolable in the free state. But what happens in this case? In this case, since this transitional metal is there, and this benzene is actually, you can think of it's a biradical, and it's binding to the tantalum center. In this case, you see the bond length is 136 picometer. This one is 141 picometer. This one is 137 picometer. This one is 140 picometers, and this one is 136 picometer. So there occurs a significant and bond length change in all this benzene moiety. So this benzene can be stabilized in terms of bonding to the tantalum center. The neodymium center can also be taken up in this regard. The coordination of benzene C6H4, which is not stable as free molecule, can be stabilized through this transition metal alkyne complex. Here you can see tantalum center is having an interaction by sigma bond between these two center. This you can think of a biradical, or you can think of this system also where there is a triple bond here. The next example, we also take up such example where a free molecule that is not actually stable will be actually stabilized by transition metal alkyne complexation bonding. So this is nothing but this benzdiene. Benzdiene is not a well-known complex. We will not hear about this. This is even benzdiene is C6H2 system. The last one, benzene, was C6H4 system. It is the abbreviated as tetradihydrobenzene. So it can be stabilized by coordination through two nickel zero centers. This unusual complex shows extensive localization of the pi electrons in the region of the coordinated carbon atoms. So here you can see this is nothing but this tetrahydrobenzene or C6H2 or benzdiene. So benzdiene having this bond length is quite short than this one, because this one having a triple bond, this one having a double bond is a 141 picometer, and this one is 131 picometer. So there is this one is having a double bond character, this one is having a triple bond character. So this compound can be stabilized even in presence of this cyclometal complex, the nickel zero compound, which is even stabilized by this PCY2 DPVY system, diphenyl phosphinoethane. This PCY2 is a chelat kind of binding. So this nickel zero center is there. You can see this P0P neutral PCY2 molecules actually bound to the nickel center. This is neutral PCY2 bound to the nickel center. They are having interaction with this benzdiene system, that is C6H2, and so that this compound can be stabilized. No compound, this organic compound is never stabilized or never isolated. Bennett actually showed this specific example in 1988. So this unusual complex shows extensive localization of the pi electrons in the region of the coordinated carbon atoms. So all the pi electrons actually localized in case of these pi systems, where they are donated the electrons to the nickel zero centers. So question 8 is what happens when the transition metal alkyne complex is reacted with a hydride transfer reagent such as sodium borohydride. So the hydride attack on an eta 2 coordinated alkyne complex leads to an eta 3 allyl complex. So this one you can see is an eta 2 alkyne complex. The eta 2 alkyne complex is actually having this pi electron interaction with the metal center. Whenever it is treated with this borohydride, what happens? This eta 3 allyl system is formed. So in the later slide, I will actually, next slide, I will show you the actual mechanism behind this reaction. So this is the proposed mechanism involving various coordination forms of C3 unsaturated unit. You see in the first is eta 2 alkyne. It is a metal is actually getting bound to the alkyne system with eta 2 fashion. Whenever a borohydride, a hydride transfer agent is there, hydride will attack on this R center, this carbon, R bound carbon atom, and there will be negative charge increment on this. So this minus charge will again be bonded to the metal center, and there will be a charge negative interaction with the metal to the sigma bond with the carbon atom. So it's a eta 2 vinyl system. This is a vinyl system, and both the carbon atoms actually bound to the metal center. That's why it's a eta 2 vinyl system. Next one, the canonical structure we may draw like this one. This double bond will come up here, this single bond will come up here, we have a double bond, and this metal will be singly bonded to the, this hydride carbon is there, and there will double bond here, and this bond will be ruptured here. That's why MCCH3 is here, because the double bond is converted to single bond now. There will be a this is a vinyl system. You can see this is a vinyl system, C minor, that is bonded to the metal center, RCHR CCH3 metal. Next example, in the next canonical form, you can see there can be a position of allyne or allyne formation can take place. So here, from a canonical point of view, what you can see, one of the proton from this side can bound to the metal center as metal hydride, and this will be double bond here between this carbon and this CH3. So it will be bound as CH2 double bond C triple bond CHR and metal hydride here, and there will be a double bond coordination or pi complex kind of coordination to the metal center. This is nothing but the eta 2 allyne fashion. Now what happens in the last case? In this case, the eta 2 alanine fashion will can occur from this bond also and from this bond also. Since this bond is more electronically rich, that's why the bonding can also occur from this double bond also. This metal hydride will shift itself to the other olefinic center. Other olefinic center. So here there are two resonance canonical form, eta 2 alene forms here. In the first alene form, you can see that this double bond is actually bound to this metal center. In the second canonical form, you can see that this olefinic bond is bound to the metal center. In case of alene, these two double bonds are actually perpendicular to one another. They are not actually coplanar. That's why whenever this will be bonded, this will not be able to be bond. When this one is bonded, this will be not available for bonding. The next one, it can be bonded to the allyl, this eta 1 allyl fashion, when you can see this hydride will then attack on this carbon center, metal hydride carbon center, and this will be negative charge on this carbon center that will be bonded to the metal center. So you can see this CHR will actually happen. So there will be resonance canonical. So this hydride is actually attacking on this carbon center. There will be a negative charge on this case. So this C minus will get bound to the metal center. This is eta 1 allyl complex, since only one carbon atom is actually binding to the metal center. But since eta 3 allyl fashion is more actually available bonding, because this is quite a stabilized molecule, this C minus will come here and this C minus will come here. And also this is total, the 4 electrons will then be canonically stabilized in the CCC framework. So all the 3 carbon atoms will be actually then be able to donate the electrons to the metal center. So it will be again forming this eta 3 allyl system. So from eta 2 alkyne complex, they are actually going to the eta 3 allyl complex. This specific example was proved by Green in 1986. Now, what is the product of the reaction? I mean, the next example, what is the product of the reaction between this PDCl2 and 2 equivalent of diphenyl acetylene? So, reactions of alkynes with metal compounds can lead to di, tri, or tetramerization of the organic ligand. So, several organic ligands or pi bonded ligands can come together and can bond the CC kind of oligomerization reaction. So, what you can see here, PDCl2 and 2 moles of diphenyl acetylene are here. The specific example was given by Michaelis in 1976, when you can see 2 diphenyl acetylene moieties are again clubbed together to form this oligomerized, this PHC triple bond, double bond CC, this cyclobutadiene kind of system. All these coprophenyl groups, and this PDCl2 is actually bonded to the other center. This one is the same as this one. So in this case, 2 moles of diphenyl acetylene will come together and oligomerize or diamerize